Hello, everybody, and welcome back to the second portion of our Bootstrap Confidence Intervals lecture. Again, this lecture is completely off book. So if you have questions, you have to read through this PowerPoint, watch the lecture video, and then send me a message on WebAssign with any and all questions that you have. You can always look for outside resources, but we want to make sure that we're creating our confidence intervals using this bootstrap technique, not with the traditional stat 1 technique that we're avoiding. So let's jump in. The first thing we're going to do is make a bootstrap confidence interval for the population mean. Let's quickly glance over what the traditional approach would have been. If we don't know the exact value of the mean, it's very unlikely that we'll know the exact value of the standard deviation, again, for the population. So as a result, we actually have to move away from the z distribution, our normal distribution, and introduce a completely new distribution, the t distribution, in order to find the standard error. So we would find this margin of error, and then we know that we can add and subtract the margin of error from the point estimate. Unfortunately, this requires us to, again, come up with or start introducing a brand new distribution and have a t distribution table in front of us. We're not going to use the traditional approach. So if you see this while looking for outside resources, this is not the approach that we're using. We're using simulation-based approach, our bootstrap technique. And again, remember from the last video, what does that bootstrapping technique mean? I'm pulling the data up by its own bootstraps. I'm going to take an original sample, and then I'm going to resample from my sample with replacement, and that resample should be of the same size as the original sample. I'm going to create what we call B of these resamples. And with the Monte Carlo, our industry standard, we're actually going to make 10,000 of them. 10,000 of our resamples, and then use the distribution from that data in order to find the confidence interval. We're letting technology bear the heavy burden here. We're going to let StatKey do most of the heavy lifting. So, bootstrap confidence intervals for the population mean. We're going to be using StatKey, and just like before, we're going to find the column that says bootstrap confidence intervals, and then we're going to confidence intervals for a single mean. Unlike the previous examples where we were doing proportions, I'm going to have to enter in a large data set here. The data set is going to be the entire samples that I create. So because of this, we typically don't want to have to enter this in manually. And we're going to see here that we can go to the Edit Data button and either just copy and paste or upload the file directly from Excel. So let's look at our first example. A trade volume of a stock is the number of shares traded in any given day. The following data in millions represents the volume for PepsiCo stock traded on a random sample of 40 days in 2014. So I have 40 data points here, and rather than entering in the 40 data points manually, I have them already in an Excel file. These Excel files, along with the PowerPoint and the lecture video, will all be available to you on Blackboard. So let me go to my Excel file here, and my first example says the stock volume. So I'm just going to edit and copy. Now we are into bootstrap confidence intervals for what? A single mean. What is the mean number of trades of this stock in millions? Now, again, as you see, there's already preloaded data here from the textbook. This is a website that comes free, but it's used in a different textbook. We are going to have examples where we use the preloaded data, but in this example, I'm going to insert my own data. So, selecting the data and then pasting in my new data set. I do have a header row here, but I don't have a first column identifier, so I can hit OK. What I always like to do is to make sure that I didn't miss any data points. I should have 40, and I do. You can see right here. The mean from my sample was 5.43, or 5.43 million trades in these given days on average. If I'd like to generate now the confidence interval, I'm going to try to do that Monte Carlo, the industry standard, which would be 10,000 Bootstrap samples. Once I have my 10,000 samples, and looks like we clicked a little bit too much, 12,000, but we get the idea. We were asked to make a 95% confidence interval. Let's construct a 95% confidence interval. Once I've generated my samples, I know that I select two-tailed. If this would like to cooperate. And 95 is already the default. So with this 95 here, I'm saying that 95% of the data falls within this interval. This is my 95% confidence interval, and I can see the values below. So what would we say? We are 95% confident that the true average number of trades on any given day in 2014 is between 4.981 million and 5.888 million. Okay. So we saw the sample mean. We made our confidence interval. Now notice here that the values that I have are slightly different than what we came up with in our stat key. That's because when I made my random samples, the first time when I made the PowerPoint, I'm not necessarily getting the exact same samples as when I make the Bootstrap samples the second time. The values are going to be approximately the same though. And I can see that. 4.976, 5.881, 4.981, 5.881. So the values are approximately the same. They're just not necessarily identical. And then again, that's because the samples that we take are not necessarily the same. Okay? This is a copy of my StatQ results the first time that I completed this. You're going to have to create these StatKey graphs for me. You're going to have to be able to take pictures of the StatKey graphs, so you're going to need to take screenshots. If you have a Mac, Command-Shift-4, and then you can drag your cursor over to where you're taking a picture of. If you have a PC, I'm sure there's a similar function. On to our second example. The Merrill Lynch Securities and Healthcare Retirement Incorporation has two large employers in downtown Toledo. They're considering jointly offering childcare to their employees, coming together to offer one childcare service. As part of a feasibility study, they want to estimate the mean weekly childcare cost for their employees. They take a sample of these 10 employees. So if I go back to my spreadsheet here, I have the data for these 10 employees. Again, we need to insert this into StatKey in order to actually work with it. So I'm just copy and pasting. Let's start at the beginning for StatKey. Confidence intervals for a mean value. We're looking at the average childcare cost. I'm going to edit my data and paste in my new data set. I still have a header row. I'll hit OK. We had 10 employees, and I see that I have 10 data points. it looks like based on my sample, the average weekly childcare cost was $98.60. If we would like to create an interval estimate, the first thing we need to do is generate samples. So I have my Monte Carlo, I have my 10,000 Bootstrap samples. I select two-tailed, and let's go back to the PowerPoint here. I'm asking now to generate a 90% confidence interval. So let's make a 90% confidence interval. That means that 90% of the data is in the interval, 10% outside, which means 5% on either tail. And again, this is the data of my Bootstrap samples. So what would I say here for my actual Bootstrap confidence interval? I am 90% confident that the true average weekly cost of childcare will fall between $95.90 and $101.30. That's what we would say. And again, you're going to need to be able to take screenshots so that I actually can see your work and see how you're getting the values. So you would take a screenshot of that. Let's go back to the PowerPoint. Using our values, what's my point estimate? Remember, the point estimate is the sample mean in this case. What did we say the sample mean was? 98.6. We made our interval. And again, we could see that our interval isn't necessarily identical, but they are going to be very close to each other. Okay, let's go on to our third example. In our third example, I'm going to take 3 samples from the same data set. But what I'm going to do is I'm going to increase the sample size each time, and I'd like to compare the confidence intervals that I get. So no need to have any type of context to our question. It's not a childcare cost or stock trading. It's just generic data. Let's look at our data set here. Again, I have this saved in Excel. I have data set 1, which has 8 values. Data set 2 has 20. Data set 3 has 30. So we're going to make 3 separate confidence intervals here. So let's start with data set 1. I'm just going to copy and paste. I'm going to go back to Stat Key here, and I'm actually going to open up 3 windows. We're making a confidence interval for the mean value. I'm going to edit my data and paste the values in. We said we were making a 95% confidence interval. Let's do that. Make this two-tailed. There's my 95% confidence interval. So let's write these values down. 86.5 to 111 and 875 thousandths. We have our first confidence interval. I want to try to compare these. So I'm going to keep this up and just open my next confidence interval in a separate tab. So I'm going to go back and select my data set 2. Bootstrap confidence intervals for a single mean. Edit my data. Paste in my new data set. I should have 20 data points, and I do. I'm going to generate my samples. We're just going to make all 3 of these intervals before we try to compare them. So make this two-tailed, and this is already at 95%. Perfect. One more time now with data set 3. confidence interval for a mean, edit my data. I have 30 data points. I made my Monte Carlo, my industry standard 10,000 samples, and selected two-tailed. Okay. So let's start with my smallest sample size of 8. I had a confidence interval of 86.5 to 111.875. We can find the width of this confidence interval just by subtracting these two values. So if we were to subtract 111.875 minus the 86.5, we can get the width of this confidence interval. Let's compare that to the next one. I have a larger sample size, and the left-hand side is larger, the right-hand side is smaller. So what's happening? This interval is contracting. It's shrinking. And as I go to my largest sample size, a sample size of 30, I can see that I'm contracting even further. What does this tell me? Well, in my example, I had a width of 25.5 for my first set, 13.5 for the second, and 10 and 433 thousandths for the third. As the sample sizes increase, the confidence interval is more precise, meaning that the width of the confidence interval will get more narrow. So if I want a more narrow confidence interval, I have to have a larger sample size in order to be within that same level of confidence. Okay. So we get the idea now for confidence intervals for a single mean. Now let's look at the example of confidence intervals for the difference between two means. So I'm going to look for the difference in two mean values between two populations, population mean 1 and population mean 2. We're going to be using StatKey in order to do this again. Let's look at this example, and we're going to use some of the built-in data sets that are already in StatKey. These are data sets that I know that you'll always have readily available, and data sets that I can assign you for homeworks or quizzes and so on. So, our data set says home prices in New York versus New Jersey. I'd like you to make a 95% confidence interval for the difference in the mean values. So it says, based on the data, which I'll show you in just a moment, we had a sample of 30 values for New York and a sample of 30 for New Jersey, and the difference between the two was a negative value. If that's a negative value, that tells me that New Jersey is actually more expensive on average. Okay? So let's take a look. I'm going to go back to StatKey from the beginning. We're still finding a confidence interval, but it's not for a single mean, it's for the difference in two means. The average cost in New York versus New Jersey. Now, when I said that there's built-in data sets, again, on the top left side, I see the data. And what do I see at the very bottom? Home prices, New York versus New Jersey. This data set is now already uploaded. These are 60 data points, 30 for each. We didn't have to come up with our own example. There's already examples here we can use. So now let's generate our samples. Select two-tailed. And our question asked me to make a 95% confidence interval. I already have this set as 95. So what am I saying here? From negative 433 or 667 thousandths to positive 57 and 83 thousandths. What does it mean if I go from a negative to a positive here? Well, let's see. If I were to draw a straight line right here, everything to the left of this line is where home prices in New Jersey are more expensive. But based on the simulation I see here, it is possible, not necessarily overwhelmingly likely. It's less likely than New Jersey being more, but it is possible that New York is actually more expensive based on the sample data that we have. So we have our confidence interval here, and we're able to interpret it. We are 95% confident that the true difference in mean values will lie in this interval from negative 433.667 positive 57.083. Again, it is possible that the New York prices are actually higher. It's all based on the sampling that we take. All right. So I have very similar values in my example. The example I did previously. Again, my Bootstrap samples aren't necessarily the same as your Bootstrap samples, but we should have very similar confidence intervals at the end. Last concept, the confidence intervals for the difference in proportions. This specifies a range of values within which the difference between the proportions of the populations may lie. So rather than looking at the difference in two means, it's the difference in two proportions. We're going to go about solving for this the exact same way. I'm going to use StatK. The only difference is I'm looking for confidence intervals for the difference in proportions. How do I know it's a proportion? It's all based on the context of the question. Let's look at our example. We're going to use, again, the built-in data set here. This is support for new gun control laws based on your gender. What proportion of men support this? What proportion of women support this? And just to switch things up, let's make an 80% confidence interval. So I have a lower level of confidence here than we typically are working with. Well, it says based on the sample data, the difference in the proportions based on the sample was 212 thousandths, which means that women were in favor of more gun control more than men, based on the sample. So let's go to start of StatK, Bootstrap confidence interval for the what? Difference in proportions, the proportion of men versus the proportion of women. I'm going to go into my built-in data set. We're not editing our own data. We're using the data that's already here. Support for new gun control laws. As I can see here now on the side, I had nearly 1,000 samples. And I can see that women, based on the samples, preferred new gun control versus men. Let's find the confidence interval. I'm going to generate my samples. Select two-tailed. And we said we wanted to be less confident this time. Let's make this an 80% confidence level. So with my 80% confidence level, what would we say? We are 80% confident that the true difference in proportions, females minus males, in that order, the order is important, right? Otherwise the sign would be different, lies between 176 thousandths and 247 thousandths, or roughly 18% to 25%. We are 80% confident that the true difference in the proportions lies in that interval. Is it possible that it's higher than 25%? Absolutely. Is it possible that it's higher than 30%? Yes, it is. Is it likely that it's higher than 30%? No, this isn't a likely result. Is it possible that men actually support more gun control over women? Well, based on my sample, women did preferred it more. But what about for the entire population? Is it possible that men preferred more gun control? Well, if they did, the difference would be negative. Is it possible that I have a negative number all the way to the left here off screen? Yes, it is possible, but it's very unlikely. It is not a likely result based on the simulations and the data that we have. Okay, and we see a similar plot that I created. We are at the end of our Bootstrap lecture. So this lecture was broken into 2 parts. On our syllabus, it's actually 3. So we combined and made this simply a 2-part lecture here. The homework for this section will be available in the upcoming days. Again, we are off book, which means that the homework may be presented slightly differently than it was for the in-book section, but we will work through it. I'm going to be responding to email questions. I'm going to be responding to WebAssign questions. If you have any questions, please let me know. Don't wait until the homework's due to try to find these values, to try to make your confidence intervals. Use the examples that I have here. Try to enter that data in and make sure that you can get to the right answers. This way, when you get to the homework questions, you're not trying to figure out how to answer the question and how to use the website at the same time. All right. Good luck, everybody. Stay home and stay safe.